What is the practical use of monads? In this episode, we're going to talk about what Haskell uses monads for, and we're going to discuss whether they are useful, and especially in practical terms. My name is Eric Normand, and I help people thrive with functional programming. So in a recent episode, I gave an example of a real-world monad. I gave the example of a book, I believe. And someone asked the question, yeah, but why does this, what does it have to do with programming? Why do we use this at all? And it's a fair question. Now, this person was Bruno Ribeiro. He wanted to understand why it's useful in code. So let's get into it. So, as a preface, because I'm not programming in Haskell very much these days, I rarely use monads myself. And I'm not really even recommending that you use them unless you are using a language like Haskell or Scala that has decided that monads is the way to do things. So I'm not a monad advocate. I just want to say that. It's kind of a useful concept to understand, but mostly because people talk about it so much that it's just to be able to participate in the conversation in an intelligent way. So people talk about it, and you should understand what they're talking about. That's like unless you're doing Haskell, right? And then you should go deep into monads because that's the way they do it. Okay. And I would say that about a lot of features of languages. Like if you were into, a Lisp, I'd say like go deep into macros, understand how macros work. But I wouldn't say that to someone doing Haskell. Like you don't need to know macros. Okay, so a little bit of history. It's going to be explanatory. Okay, so like this is why Haskell uses monads. How did it get there? So Haskell has this goal of functional purity. Okay, there's even the slogan of avoid success at all costs. And that's like a cheeky way of saying we're not going to make compromises for, people say, oh, to be practical, you need to have side effects and you need to allow them. They're saying, no, we don't want to do that. Especially at the beginning, before we really understand what we have here. And I appreciate this because there were a lot of languages that already had side effects, had made that compromise, like ML. And Haskell had a different goal, which was to be a kind of lingua franca for pure functional programming for researchers. But, at the same time, they wanted to do effects. They needed to. At first, Haskell programs would just like calculate something and then, the last thing it would do is just print out the answer, right? So it wouldn't be able to like interact with you and like read a file, things like that. It would just be like input at the beginning, run the program, output, print it out. So eventually they started adding, you can do effects in this way. There was this IO type that contained the effects, but when you're doing I/O, the sequence of steps really matters, right? Like you need to be able to say like first read the input from the user and then calculate the answer and then print it out. So you can't do them in a different order, right? So you need some way of guaranteeing the order. In most languages, that is a basic language feature. The steps are executed in order. But in Haskell, it's a lazy language, and you could do it. You could make it so that you wouldn't you would execute them in order, because there is kind of a dependency. Like once you read the input, you can't get the input before you read it. So there is some dependency there, but you'd have to like trace, like write the code so that it was like passing the results to the next function, and then that would be, so you'd have these like deeply nested functions. It was awkward. Okay, like the longer the sequence, the more nested you'd have to get. It was not pretty. So they were looking for a solution to this, and Philip Wadler wrote a paper that showed how you could represent a whole bunch of things from imperative languages, like input and output, state, so mutable state, and exception throwing and catching exceptions, using monads. Now this was a concept from category theory, and he was showing how you could take this and apply it in Haskell. So then Haskell, people like it, still a little awkward, so they add a notation called do notation. In Haskell, you type do, and then you go to the next line, and you can just start writing a sequence of statements, and it will convert that into a chain of monadic bind calls. Okay, so it's a syntactic sugar, but what it allows you to do is write this nice imperative-looking sequential code. There's even a version of it that has semicolons so that it looks like C, right? And you can do all your I/O, and it runs in order, and it's really nice, right? It feels very much like you're writing imperative code, but under the hood, it's all functional. Okay. And we'll get back to that. Like, what does it mean that it's functional under the hood? We'll get back to that. But just suffice it to say that they did not violate the purity goals. The language now could do I/O. It was convenient to write sequences of steps when you needed it, and it was, pure. Okay, so Haskellers, when they're, learning Haskell, they have to learn monads. I had to learn monads when I was doing Haskell. It just kind of comes up. There's a type called I/O, and this type is where, it's kind of where, it's like the box that all effects get pushed into, right? So all the reading of files and writing to standard output and errors, they all get kind of thrown into I/O. Error handling, that is. It all gets thrown into I/O. Okay, so if you're not in I/O, it's very pure. Everything is pure. It's lazy. It's all nice. And then you get into I/O, and now you're in sort of what I would call actions, right? So outside of I/O, it's all calculations. Inside of I/O, you got actions. And as you know, actions can be calling calculations, right? So it's I would say if you're going to draw one line, that's the line to draw. The stuff that's pure, and then the stuff that's I/O. That's great. And if you turn that into a monad, that type into a monad, it means you can use do notation, and you have this nice sequential thing. So that's, you don't even have to know about monads at first. Like, you just say, oh, this do notation, this is where I put all my imperative code. But the thing is, like, in this paper, monads were shown to be useful for other things besides just I/O. Okay, so I said before, it can do state, so mutable state in a pure way, because it's not really mutable. It's not like it's still using immutable data structures. It's just the name of the value through those sequence of steps stays the same, but the value can change. It's like a mutable variable, right? So you can create mutable variables using a monad, okay? So you can also create error handling or custom error throw catch situations using a monad. There's other monads, the other things you can do, continuations, that kind of thing. But they were shown to be really useful for this. But then it brings up this question. Is that useful? Because these are things that other languages already have. They have mutable state. They have sequencing of input and output. Why is that useful? Alan Kay has, on the record, said that this is a kludge. Like, you're trying to stay functional in a situation where you don't need to be functional. At the same time, it is a pure way of doing these things. And because it's pure, you get all these other benefits, like it's lazy. It's since it's mathematically rigorously defined, you can do algebra on it. You can, because monads are a category, you can like rotate it into another category. I don't know how to do all that stuff, but it's high level stuff that is possible because it's pure, right? Like, because you can understand it at a syntactic level, has, mathematical laws. There's all this stuff that you can do with it that I don't honestly quite understand. It's not stuff I do in my day-to-day, but I could also imagine using a library that relied on that and be thankful that I was inside of that monad. So you got these two sides of the same situation. One is like, well, we already had those things in our language. We already had mutable state. We already had side effects. We already had sequencing of steps. We had all that stuff. So we don't need them. We don't need monads. But then at the same time, you have this other realm that you can't get to if you don't use the monads, right? So this is the trade-off right here. When I see people, in Clojure there's a library where you can do monads as well as you can do them in Clojure, and I always wonder, like, why? Why do you want this? What is the appeal of bringing monads into a place where we don't, you already have all the things that people are using monads for, and it just feels a little bit like just chasing after Haskell, like, oh, they use it, so it must be good, so let's do it ourselves too. Haskell uses monads so much primarily because of a self-imposed limitation of purity, and so now they need something to make it so that they can have the mutable state, the sequencing, things like that. Okay. There's other things that monads are useful for. I'm not saying that. But this is their primary use, right, on a practical level. Okay. Right. So just a short recap. If I'm in Haskell, monads, let's use them, because that's the way you do things in Haskell. I know in Scala, in the effects systems, they use a lot of monads as well. They're trying to get to this purity that they don't quite have as much as in Haskell, right? Because the language does allow for mutable stuff and things. But they're trying to get there with effect systems. But if I'm in Clojure, if I'm in some other functional language that doesn't use them, even ML, right? I wouldn't want them. I wouldn't like say, oh, we need them or we can't continue. All right, so what is the practical use of monads? Like, how is it that monads allow for you to sequence these things? All right, so this is going to be the last thing we talk about, but like, I haven't really explained why monads let you do this. Okay, so now I'm going to try. So let's say you're doing imperative programming. In imperative programming, and we're just going to simplify the model a little bit. We're going to say that imperative programming, you have subroutines, you define these subroutines, and then the subroutines are calling other subroutines, right? So it's subroutines of subroutines of subroutines, until you get to some built-in functionality, right? So a subroutine is just a sequence of steps, and it's either, it does a basic thing or it calls another subroutine. And that's a pretty basic model of imperative programming. So you have these nested, subroutine things, but what the CPU expects is a linear sequence of steps. What do I run next? What do I run next? What do I run next? So in like an imperative compiler, it would probably compile it like do this, do this, do this. Now do a go to and jump over to this subroutine and do that. Do step 1, do step 2, do step 3. Oh, look, step 4 is another subroutine call, so jump to that subroutine and continue like that. And then you would have a stack so you could come back out of the subroutines, right? But if you notice this nested structure, you could linearize this by doing a monadic join. So I have a subroutine that includes a call. Subroutine A includes a call to subroutine B, and I do it. So it's a subroutine of subroutines, and I do a monadic join that becomes a single subroutine, not nested, but like it's just steps, right? So this allows the sequencing of all the steps for the execution, right? It doesn't go straight to the CPU, obviously, but it becomes a linear sequence of steps, okay, because of that monadic join. You can go listen to the other episode where I talk about monads in more depth about how they're defined. But it's a list of steps inside of a list of steps. It's a list of steps. So you can do the join and boom, it becomes just a single list of steps. Right. So that is what gives you the sequence of that the CPU needs. Now, here's the thing. You need some kind of branching, right? You need some kind of like, well, I'm going to execute this subroutine, and if the answer is 0, I'm going to do this subroutine. But if the answer is 1, I'm going to do this subroutine, right? So you don't even know what branch you're going to go down until after you've executed that step. This is where the bind comes in, because you can have a function that makes that choice, right? I'm going to execute something like database query, let's say, and I get the answer 0. So my function is going to look at that answer and return a subroutine A or a subroutine B, depending on the answer. If it returns 0, it'll return subroutine A. If it's 1, it'll return subroutine B. And then the join will execute, make that a linear sequence of steps. So you don't know the steps in advance because you're using bind, not just a strict join. Okay, you don't know the sequence of steps in advance because there's going to be choices that you make along the way, that your program makes along the way. Okay, so you're not going to be able to just linearize it. You have to execute it one step at a time, and some of those steps are going to call, some kind of side effect, and that's going to give you an answer that you can make a decision based on. Okay, so that is a property of monads that you can't really, because of the bind, you can't really expand it all the way. The bind includes a little decision in it. Like, what do I do next? Now that I've got this answer, what do I do with it? So that's kind of a limitation of monads, very well understood limitation, that it's not a pure data structure. It has functions in it that will be required. They can't run until thing executes. But it's all built in there, right? So you're doing these little pure calculations of like, what subroutine do I run next? And then that subroutine gets returned and gets kind of linearized in the next sequence of steps. So it doesn't have the whole future. It just has one at a time, like that. Okay, so that's, I think, enough about monads for the moment, at least. We're talking about whether they're practical. Like I said, just to recap, they're very practical in Haskell because of the choices it's made, its philosophy of not making compromises. Something is doing the effects. Something has to be doing the effects, but they're pushing it off as far as possible. It's the runtime that's actually running the effects. I don't use monads much myself. I mean, unless I'm doing Haskell or something. And so I'm not recommending them. Philip Wadler was the one who brought monads from category theory into Haskell, and it lets them do something that looks like imperative code with just a little bit of syntactic sugar, the do notation. And it lets you reproduce all these things that you have in imperative languages, like sequencing steps and mutable state and stuff like that. Okay. If you like this episode, you should go to lispcast.com/podcast, and there you'll find all of the old episodes. So many. And you'll see the audio, the video, and the text versions of all of them. You'll also find links to subscribe and to get in touch with me on social media. Please do subscribe, because then you'll get all of the future episodes. Awesome. My name is Eric Normand. This has been my thought on functional programming. Thank you for listening, and rock on.